Hi, everyone. In this video, we're going to be talking about trees. And when I say trees, I don't mean the plants. I don't mean the things that provide shade and air. I'm talking about a mathematical graph theoretic version of a tree. And before I get into what that is, let me pay some debts, so to speak, on things I haven't actually formally defined, but will do so now. So a path, we've seen this word attached to other words, so like an Euler path, a Hamiltonian path, but a path just by itself is a walk on a graph that doesn't repeat any edges. And there's varying usages of this terminology, but whenever I say a walk or whenever I say a path, I will be meaning that it will always start and end on different vertices. Okay, and so just by itself, it doesn't have to hit every edge. It doesn't have to hit every vertex. It can repeat vertices. So it doesn't have to be an Euler path. Doesn't have to be a Hamiltonian path. It's any walk that just doesn't repeat any edges. And so an example, if I just draw a little bit, tiny little thing here. An example of a walk is AB. Sorry, this is a path, just AB. You start at A, go over to B. You don't reuse, you don't use any, you don't use every vertex, you don't use every edge. It's neither Hamiltonian nor Euler, but it's still a path. And then along with path, we have circuit. So this is any walk on a graph, almost the same definition. That doesn't repeat any edges. And starts and ends on on the same that's not how you spell vertex. Okay, and so we have Hamiltonian circuits, we have Euler circuits. These are all examples of circuits, but an arbitrary circuit, it can repeat edge or it can repeat vertices, not edges, but it can repeat vertices, and it doesn't have to use all of the vertices, and it doesn't have to use all of the edges. It just, as long as it doesn't repeat any edges, it's a circuit. And a network, this is a lot of times you'll see this in computer science or other applications. A network is just another term for a connected graph. And so in our example, a few videos ago, this was the graph that modeled friendships in a previous video. We had one vertex per person and an edge between two vertices if the corresponding people are friends. Then we had enough friendships to make that graph connected. And so that graph was a network. And that's also why you have the term social network, because when there are many, many users, you will always be able to find some path. You'll always be able to find some trail of connections. I am friends with so-and-so who's friends with so-and-so, et cetera, to match you with any two people. This is also sort of the idea of 6 degrees of separation. The more friendships you have, the closer your connection will be. Okay, what do any of these have to do with trees? Well, let me first draw a little tree. So you've got roots in the ground, and then you've got a trunk that goes up, and then you've got a bunch of branches, and all those branches have little branches of their own. And then all of those branches, little branches might have branches, etc. And I'm not going to draw the leaves, but okay. And so this is sort of the skeleton, quote unquote, or a naked tree. There's just no leaves. And so notice there are no loops or circuits, right? If I'm starting here, if I'm going along what I've drawn, there's no way to come back to here. Trees don't loop in on themselves. Okay, and so we're going to turn this picture into a formal definition. So a tree is a connected graph or a network that has no circuits. Okay, so let's look at some examples and see whether or not they're trees. So I'm not going to bother label. Well, I'll label the vertices. Why not? Okay, so if I do this, okay, so take a second, pause the video, see if you think this graph is a tree or not a tree. Okay, hopefully you thought about it. This is not a tree. Why isn't this a tree? Well, we have a circuit, namely A, B, D, C, A. So if I start at A, I can go over to B, to D, to C, and then back to A. I've not repeated any edges, and this is certainly a walk, and I started and stopped at the same place. This is a circuit. So this graph has a circuit, so it's not a tree. Okay, now let's draw another one. And for this one, because it's larger, I won't bother labeling everything. So this, take a second and think about it. Think if you can determine if this is a tree. Well, yes, this is a tree. Okay, why is it a tree? Well, we're going to see a way to determine more easily if this is a tree. But the fact is that this doesn't contain any circuits. If I start here, for example, then I have no way back, right? Anywhere I go, if I go here, I'm just going to sort of expand outwards. There's no edge that's coming back over here. And also, compare this with an upside down version of our drawing here. It kind of looks like it, right? It sort of branches out at each step. And I could have even, you don't have to draw two. I could even, get even crazier and draw, a bunch of these little offshoots, but this is still a tree. I still haven't closed any circuits, and it's still a tree. And so determining if a graph is a tree is not always super easy. So for example, if I draw something like this, is this a tree? Well, let me draw it a little better. Oops. Is this a tree? Well, it's kind of, oops. I want to do this. Yeah. Is this a tree? Well, maybe. I mean, it's not even easy to tell if it's connected because we have edges that overlap, but that doesn't mean it's connected or not. So it's kind of hard to tell. And so redrawing this, you can redraw it in the same way, right? If I draw these three edges, I can draw them like so. So this edge is this vertex, this vertex is this vertex is this, and the edges correspond like so. And so then we can also just draw this other piece right here, minus that. We can draw it like so. Right, so these are the same things. I've just redrawn it in a different way. This is not connected. So it's not a tree. It doesn't have any circuits, but it's also not connected. So it has to be connected and have no circuits. So how do you determine, right? If I just give you a jumble of edges and vertices, how do you determine if that's a tree? And there are some other criteria that will tell you when something is a tree that we will get to in a future video.